So given an implication like phi implies psi, there are a few different ways to flip it around. And depending on how you flip it around exactly, there are some logical fallacies associated with equating an implication with different flipped around versions. So the first one is the converse. The converse is what you get if you swap the hypothesis and the conclusion. Remember, hypothesis is the left side of the implication and conclusion is the right side. So if you swap them, then you get what's called the converse. Another thing you can do is not swap them, but negate both the hypothesis and the conclusion. So like this. Instead of swapping, just negate each. And that's called the inverse of the implication. And another one is to do both swap and negate. So take the inverse of the converse, or the converse of the inverse, and that's called the contrapositive of the original implication. So not psi implies not phi. Okay, so let's do an example and think about whether it should be the same. Let's think about whether the converse or the inverse or the contrapositive should be considered the same as the original implication. Okay, so let me fill out an example. Okay, let's say phi is you are coughing and psi is you have COVID-19. Then let's think about phi implies psi implies phi, and the other two. It's not the case that phi implies it's not the case that psi, and not psi implies not phi. So how would you read each one? So this one says if you're coughing, then you have COVID-19. So this is asserting that anyone who coughs must have the virus. This one, on the other hand, says if you have COVID-19, then you're coughing. So anyone with the virus must be coughing. Do those feel like they're the same? They really shouldn't. They should definitely feel different to you. If it's true, let's think about this one. If it's true that anyone who has COVID-19 is coughing, that if you have COVID-19 then you're coughing, then it still leaves open the possibility that you could be coughing for a different reason, right? This says if you have the virus, then you're coughing. But you could be coughing for a different reason. And that would not contradict this. On the other hand, this one says if you're coughing, then you have the virus. It rules out that you could be coughing for any other reason. But with this one, it still allows you to have the virus without coughing. It could still be true that coughing implies you have the virus, but you could be not coughing and still have the virus, according to this one. Let's think about these two also in relation to them. So this one says if you're not coughing, then you don't have the virus. You don't have COVID-19. This one says if you don't have the virus, then you're not coughing. So for similar reasons, these two are definitely different. But I'd like to convince you, or I'd like to make you think about and maybe convince yourself that these two are actually the same. And these two are also the same. Even though this one is different from this one and is different from this one, I want to convince you that the greens are the same and the reds are the same, even though the greens are different from the reds. So one way to try to make it sound clear is just to read them out loud. So you can just read them out loud to yourself, or I will read them out loud now. This one says, if you're coughing, you have COVID-19. This one says, if you don't have COVID-19, then you must not be coughing. Hopefully those sound the same, at least. Another way to think about it is think about it as applying to a group of people. So for this to be true about all people in a group, it would have to be true that anyone who's coughing has COVID-19. So it would have to be true that of the coughing people, there's a... Sorry, it would have to be true that if you take the collection of coughing people, then that's a sub-collection of the collection of people who have COVID-19. There might be other people who have COVID-19 who are not coughing. So something, what I imagine is something like this for the green situation. There are coughing people, and that's a sub-collection of the people who have COVID-19. COVID-19 havers. That's kind of what the green ones are saying, or that's what this one is definitely saying, right? If you cough, then you have COVID-19, but you could still have COVID-19 and not be coughing. Now think about this one. If you don't have COVID-19, then you must not be coughing. So if you don't have COVID-19, that means as a person, you're someone who's not in this large circle, not in the large group. Therefore, of course, you cannot be in the small group. So hopefully those feel very similar to you. And the red situation is kind of flipped around and is definitely different. In the red situation, we're saying if you have COVID-19, so if you're in this group, COVID-19, there's probably a more proper way to say that you have COVID-19, but whatever. If you're in this group, then it follows that you're in the larger group of possibly larger group of coughing people. Now, what's the relationship between the two greens and the two reds? Each one is the contrapositive of the other. So this one is a contrapositive of that. This one is the contrapositive of that. Okay, now let's look at an actual theorem that says that when you contrapose an implication, you get the same implication. Or not a theorem, but a logical rule. So here is derived rule 14 telling you that an implication is equivalent to its contrapositive. So phi implies psi is equivalent to not phi implies not. Not psi implies not phi. So let's prove this. First of all, the kind of thing we're proving is an if and only if statement, an equivalence. So that means we have to do basically two proofs, the proof of one direction and the proof of the other direction. So I'm going to use the arrow symbol as my heading for the different parts. So let me start with the first direction. That means I need to assume the left side, so assume phi implies psi. And then my goal is to prove the right side. So now my goal has become to prove this. And maybe I'll write my goal in blue. When you're writing an actual proof, you usually wouldn't write your goal. Sometimes you would. Actually, I'll write it in white because I will write it. I'll make it part of the proof. We must prove. You can write your goal like this by being clear about, the reason you're saying a proposition. Here I'm going to say not psi implies not phi. But I'm not just writing this down. If I just wrote this down, it would look like I'm asserting it, and that would be wrong. I'm writing these words that say we must prove. That means I don't think I've already proven it. I think I need to prove it. That's a common mistake I've seen in Math 8, is people will write down the thing they want to prove just to remind themselves that this is what they want to prove. But they'll write it as though it's an assertion. Okay, so we want to prove this implication. So let's assume the hypothesis. And now our goal is to prove this. So now we must prove not phi. So let me highlight what it is I have, what pieces are in play, what pieces are available for me to use, or what cards are in my hand, if you like. I have this, and I have this. These are the two things I have to play with. Now, what can I do? So there is modus tollens, one of the earlier rules that allows you to prove not phi, but I actually don't want to use it. I sort of just showed you that earlier to give you a better feel for how implication works. But that itself is a derived rule, so I'd rather avoid using it. What I'm actually going to do here is, so imagine you don't have modus tollens available, you just have modus ponens and basic rules like proof by cases, proof by contradiction. What can you do here? So I have not phi. How in the world can I make use of any of this? We can do a proof by contradiction. So let's assume that phi is true and see if we can prove not phi. So let me start a new paragraph for the proof by contradiction. Suppose, for the sake of contradiction, that phi is true. Then if I can get a contradiction here using the 2 bits that I have and this new bit that I now have, then I can deduce not phi. So hopefully, the goal here is to say a bunch of stuff and then reach a contradiction, represented by these exclamation points. And then, if I succeed, then I can say, therefore, this new card that I introduced phi must not be true. Therefore, not phi. So let's see if we can fill this in. Okay, now I have phi, and I have phi implies psi. So using basic, just modus ponens, since phi implies psi and phi, we have psi. So that's just using modus ponens. And look, we have a contradiction. Now we have psi, and we already had not psi. Then psi and not psi. A contradiction. And so that completes the proof of this half of the overall proof. So we've completed the proof of one of the 2 arrows contained in this double arrow statement. Let's work on the other arrow now. So now we're going to assume the other side, which was, I think it was not psi implies not phi. And then we must prove that phi implies psi. So for doing that, assume phi. Now my goal is to prove psi. And same strategy. Suppose, for the sake of contradiction, that psi is not true. If we can get a contradiction, then we will know that psi must be true. So the goal is to reach a contradiction, and if we do, then I can end and say, thus, psi. Then I'll be done. So where will the contradiction come from? Well, I have this, and I have this. So I can apply modus ponens. It's basically the same proof, just with symbols kind of swapped around, right? And if you're typing your proof in LaTeX, then one advantage is when you're in situations like this, you can copy and paste and just change some symbols around. But make sure you proofread after you're done writing, and that you did actually change all the symbols around to make it make sense. So here, since not psi and not psi implies not phi, we have not phi by modus ponens. Thus we have the contradiction phi, we had phi here, and not phi. So that proves the derived rule for contraposition. If you have an implication, you can always contrapose, and that will be an equivalent statement, a completely equivalent statement. And it's a logical fallacy to think that if you have an implication, then you can just flip it around, take converse, and to think that that's equivalent. That would not be equivalent in general. So one more comment here about what contraposition can do. So contraposition helps you with a single arrow, right? It tells you if phi implies psi, then you can flip them around and negate both, and that's just another implication that you also have. But it can also help you with double arrow type statements, equivalences, because a double arrow is actually just the two single arrows. So suppose you know that phi, if and only if psi, then you also know, what that means is you know this, basically. That you have both single arrows. That's how you use an equivalence. That's what an equivalence is giving you, right? The two single arrows. Each one can be contraposed. So if you have this and this, so I'm not writing a careful proof here, I'm just trying to give the idea. Each one can be contraposed. So you can rewrite what you have like this. And that's two single arrows, so you actually have this one double arrow with the negations. So once you've got contraposition working, then for a double arrow, it sort of tells you, well, you can just stick on negations, and you still have that double arrow. And that should make sense. Phi is true if and only if phi is true, if psi is true, should sound the same as phi is false if and only if psi is false. After all, the equivalence is basically just saying that phi and psi either hold or fail to hold together. So they're either true together or they're false together. So yeah, of course, if you look at the negations of both of them, then those are also either true together or false together. And what I'm describing is right here, derived rule 15, about inverting an equivalence. If you have phi if and only if psi, then you can negate both, and you have that equivalence too. And there's a more careful proof there.